So now we are working on 3.2, so I want to introduce a few important things we are planning to do. It's not a definite list. We still can add things and modify things, but just to show you what kind of things we are planning. Bytes API. There's several things that not so much happy with Bytes API currently. First, the goal of the standard library is to make things easy and at low performance cost. The idea is that if it's somehow if it's something we give as a standard API, but it's too slow on every platform, then people will just kind of fall back to platform-specific code. So they will not use the standard library. So we want to provide classes that are very high performance, whatever the platform you are on. It is quite important for us. And the Bytes API currently, we have several API for that. We have XEO bytes. We want to complete it to have all int and unsigned int API to access for 8, 16, 24, and 32 bytes. We added, I think, float and double support in 3.1 as well. And so we want to be able to use bytes not only as byte by byte, but more like 2 bytes or 3 bytes, 4 bytes accesses. And we want to have something that will be similar to JavaScript typed arrays, which are the kind of standard for this kind of thing, which is a kind of a view of a given part of the underlying bytes and be able to access this view. It's an offset somehow. It's an offset in the data and a view of this, and you can have several views on the same data. And I think this is kind of thing that will very enable people to build more efficient software when you manipulate binary data. It's quite necessary. So maybe JavaScript is the right way to go, and we need JavaScript actually support, and it's one of the important platforms for Haxe, one of the most important, maybe the single most important at the moment. I don't know if it's the most used, but well, maybe it's the most used. So we want to have something which is quite near from that, and at the same time we have to look at what the different platforms can provide and do something that is somehow Haxe specific, but still unable to convert easily between the different platforms. So it will be a set of abstract class that maps the native class and that provide high performance access for bytes manipulation. Unicode support was something that was requested several times. It's actually quite a complete one, so I will go into quite extensive and hardcore details about that. Sorry about it. X strings are array of chars. Okay, that's the same whatever the platforms. The problem is that the definition of char itself is per platform at the moment. A character is, for instance, in C++ or Neko, if it's an int, it's 8 bytes, so it can be ISO and C, whatever. It's just kind of raw characters. In GS Flash, it's 16 bytes, so it's US2, S2 encoding. In Java, it can be user SS2 or UTF-8, depending on the JVM version. In C#, I think it's US17. So it starts to get complicated because each platform has their own native encoding, and especially the C++ and Neko one is quite old-fashioned. So we want to fix that. We want to do something. So I was asking myself, what is a string in the first place? So at very low level, a string is just a memory zone, so like an array of bytes, a lot of bytes, so value between 0 and 255. And the encoding is implicit, which means that it's not stored in the bytes themselves. So if you don't know the encoding on the string, you can't read it. Of course, you can try to guess, maybe. There's ways to do that, but you can't be sure, okay? The storage of the chars in the string, in the memory, depends on the encoding. So that's the way you can't read it. Let's see our various encodings that are available for strings. First one, quite easy, is ANSI. ANSI has a character range of, let's say, from 0 to 7F. So it's like from 0 to 127 in decimal. That's a half byte somehow. So every byte every character takes a single byte, no problem. And I put here the complexity of access, which means that since it takes always 1 byte, if you want to get to the substring, for instance, from the 10th character to the 15th, you just go to the 10th bytes and 16th. It's very easy. You just have immediate access to the length and all the values. The length is the number of bytes in your string. That's all. Okay? It's very easy to. Very fast. Of course, the problem is that you cannot store much characters with this. Basically, it's just like A, B, C, D, and in different case, and the numbers and a few punctuation characters. So this is quite good, but not insufficient. Then something was introduced, of course, for European, which is called ISO. So there is different kind of ISO codes. So it extends ANSI to go to, I think it's ASCII actually. Well, maybe not ANSI. Well, it extends ASCII to go up to the end of the byte, and all these extra characters, which are above 7F, are bounded, for instance, to a French accent, A, and all the accent characters. And depending on the encoding, you get different characters. I think, for instance, in Europe, we have it was the most common, which is ISO 99 or something, 9979, no, 8879 or something, which is the most common encoding. And then you have one for Cyrillic and different thing. Okay? So the problem is that, of course, depending on you have to know the ISO code page, and depending on that, you get different characters. So it was very complicated. And I'm not talking about Japanese encodings, which are much more complex. So at some point, it was very, very difficult in the world to understand what kind of string and what kind of encoding was using. So the people kind of group together and create something which is called Unicode. And Unicode say, okay, we will define exactly which are the we allocate for each character a given unique code, which is the same for whatever the encoding. And then we will have different encoding which can represent this code or parts of this code. Okay? So, of course, to make things easy, they say we will keep ASCII the same. So the ASCII has the same code it had before, which are in the range from 0 to 7F. Then we, of course, for all the extra chars, we allocate special codes, and people can use different encoding to kind of store this code, these characters, in the string. I'm not yet hardcore, okay? UCS2, okay, sound is better now. UCS2 is the difference is that it have 2 bytes per character, which means that you can go from 0 to something like 6,500,000 and it's 535. Well, and so it's 2 bytes per character. So it's quite easy because you just takes 2 bytes. The drawback of UCS2 is that if you want to store ASCII, for instance, a big text, it takes twice the memory. And if you want to store it in the file, it's not really readable by most of the text editor because you will get 1 ASCII char and 1 0, 1 ASCII char and 1 0, and 1 ASCII char and 1 0 because it takes 2 bytes, okay? So they introduced something which is called UTF-8. UTF-8 is a bit different. First, it can encode a lot of different characters, much, much more than UCS2. So all the kind of very, for example, I don't know about the different language, but you know they have a different, Unicode is very large code page. So you have very like things that very whole language that are not used anymore, but they have their own kind of Unicode page. So you can use it with UTF-8. And the nice thing about UTF-8 is that it takes the good thing is that it takes for ASCII is exactly the same. It doesn't change anything. So it's only when you start getting beyond ASCII that, for instance, if you go in the codes a bit up, for example, in European accents, in general, you will take 2 bytes. And if you go in Japanese, you take 3, 4, 5 bytes. And you can go up to 6 bytes for the high range character. Okay? So it's a variable bytes encoding. Okay? So in general, it's very used for HTML, for storing files on the hard drive, because basically if you just have ASCII for all the most of our countries, especially Asian countries, it's really easy to store. The drawback is that since it has a variable length of char as variable length, if you want to go, for example, to the 10th character, you don't know exactly what will be this position in memory first. You have to read the whole string and decode the whole characters. So you look at the first one and you look if it's a 1 or 6 bytes. So you decide, you look at the bytes, and then you go on the second one, and then you advance in your string. And it takes, for instance, if you want to know what is the last character of your string, if you have not optimized for this, it will go through the whole string to find the last one. Okay? So if you have very big string, if you load, for instance, 100 mega or 1 gigabyte string in memory, all the operation will be very, very slow. Okay? Which is a huge drawback for runtime performances. And then you have UTF-16, which is a bit different. The idea is that you can encode less character range than UTF-8, but still a lot. So I guess it's still practical. And you have this specific character range between D8 and E0, which are not bound, which is not, you cannot encode with UTF-16. But it's good because Unicode says they have reserved this character range for UTF-16 encoding. So it means it will not be allocated to any character point, which is good news somehow, because it enables to encode, to use this kind of code specific to kind of escape some values. Like you have, if you say the backslash, for instance, it's kind of, you use this as a backslash somehow. So basically in UTF-16, you have 2 bytes per char, but when you have one of these special characters between the D8 and E0, it means that it will be some kind of escape characters, and in that case, it will take 2 other bytes for encoding the character. So it's either 2 for most of the characters or 4. The problem is that, of course, it's still the same problem that as UTF-8 is that it's odd of n. It's like you have to go through the whole characters to know. But somehow you can still, if you have some kind of additional tag, you can know, for instance, if the string has these characters or not. And if you tag the string as not having that, you can somehow have 2 different implementations. So there's kind of 2 characters are called surrogate pairs. That's the official way of doing that, telling that. So that's somehow the state of encodings in memory. So yeah, UTF-8 is good for storage HTML. So if you go into the details of UTF-7, from 0 to D7 same as UCS2, from E to FF is same as US2. From this point it's surrogate pairs, so you have 2D chars, and these are invalid code points. The problem is that, okay, Unicode says they are invalid code points, but they can still be produced by other encoding because nobody forbids you from accidentally producing these code points in other encoding. And if you produce the code points accidentally and convert to UTF-16, then you get an invalid UTF-16 string, which is kind of annoying. Still with us? Okay. So what to do from now in Haxe context? That's a bit complex, because you have all these different functionalities with pro and cons. There is no clear winner in the, depending on what you want to do, it will be different. So first, thing is that we should provide X, UCS2, UTF-8, and SX16 classes that manipulate string using this encoding. That's the first step. That is important. Check that there are and conversion function between these. And we have to check that they are cross-platforms, that work everywhere the same, that they are kind of good enough. And then check performances, of course, to ensure that they are not like too slow. And most likely, we'll switch to UCS2 as default because it has this nice access time. It's quite easy to implement because it's only 2 bytes by SHA. And it's also nice because it was JavaScript and Flash used, and especially JavaScript. We don't care so much about Flash anymore. But it means that we have something that is quite compatible with one of the most popular platforms today. When will it happen? This switch to UCS2 by default is still to be told. It will depend, I guess, which speed we advance on these different things and what was the feedback we get on this. So it might be 3.4 or 3.0. Maybe it's quite a big change, so it will require a major release for that. But we could make it optional. I'm not sure yet. We're still talking about it. Not sure yet. So tell us if you have a better idea. Okay? A few other things. We want to do in 3.2. We want to allow build in macros, which is something that was asked for a long time. I tried to do it the first time and completely failed because you have this kind of special things when you run a macro inside a macro, and so things get complicated from here. So basically we have to kind of create a separate macro context that will run into the macro context, and in case you happen to have a loop, then it's your fault, okay? I will not support it. We want to move SPOD outside of XDB package because we feel it's not exactly displayed there, and we want it to be updated more often and to have more like tools built on it. So more like often release cycle. We want to disable the Neko VM bridge, which is used to implement some part of the macro subsystem, which means better support for irreg and XIO process in macros. We want to work a bit on date also, like something that we asked to, like local versus UTC times. It's the data API is very rough at the moment. And for this we need to give feedback because it's kind of business-oriented stuff. And I make games, and in my games I don't remember using date at all. So what exactly do you need and how it should be structured, and then we can look at the API and try to implement it based on different platforms. Global optimization path is also something we want to achieve. At the moment we have a different thing. You have inlining, we have several optimizations, just have constructor inlining, if you know about it. It's a way to, you create an instance, for instance, a new point, and because its constructor is marked as inline, if it doesn't, the instance itself does not escape the local function, it will just replace it with actually the variables of the instance. So you get, you don't allocate at all the object, which is very nice for performance. And so we have all these optimizations, and they are actually somehow optimized by themselves. So it means that they don't interact well together. So we want to have something which is similar what very low-level compiler do, such as GCC or this kind of thing, that we translate the whole code into a low-level representation, just as SSA or these kind of things, and that will optimize things and then turn it back into an expression to be sent to the backend. So that's quite a complex thing we want to do here, and but it will involve very a lot of different optimizations. Actually it will maybe not be noticed because on some platforms, because the just-in-time sometimes does this kind of optimizations, because for instance, if you talk about constant propagations, which is a way, for instance, you have value variable and you say equal 20, and you don't modify at all the value in the code, but you use it several times, constant progression can remove the variable declaration entirely and put the 20 value at different place instead. So it kind of, if you have a 20 divided by 2, for instance, it will replace it by 10 directly. So you can have this kind of high level and quite performance optimization. Sometimes the just-in-time, depending on the platform you're running on, will do that for you, sometimes not. So we want to ensure that it will be done anyway using a global optimization path. And there are some things we can optimize that the just-in-time cannot optimize because we know more about the code we are generating than the just-in-time does. And a new thing, the Python target. We have a Python target on Git at the moment. I think it's passing all the unit tests. Yeah, can you confirm? Yeah. It's passing all the unit tests, working very well. So if you're a Python fan, you can just give it a try and report us all the bugs you can find. So, well, it's a more and more target for Haxe. I think it's always good to have targets that people can find usage for that. Well, as long as it's not COBOL, it's fine, or Visual Basic.